Hello everyone, welcome to the electromechanical devices course. In this video we're going to start new chapter, which is chapter 5. This chapter we're going to focus on the steady-state sinusoidal analysis of electrical circuit that would include the resistors, the capacitors or the inductors in one electrical circuit. If I just give you a summary, very quick summary of what we already discussed through this chapter, this course. In chapter 2, we already discussed the analysis of resistive circuit that include just resistors, and we found that, and we discussed different methods, four methods of doing analysis for this type of electrical circuits, and we found that it is much more simple and easy for us to do this analysis because we do have proportional relation between the voltage and the current over the resistor. Then we discussed through chapter 3 the inductors and the capacitors and these electrical elements, and we introduced them as controllers that they do control the current and the voltage distribution within the electrical circuit. Then we moved to chapter 4 to know how we can do analysis for electrical circuit in the time domain, which is the title of this chapter was the transients basically. And if you remember that we discussed that the electrical circuit, it should be, or the current or the voltage through the electrical circuit is going to be represented by a general function through that it would take this approximate form, like we're gonna have here the current. We focus on the current for a given voltage source in the time domain. So we're gonna end up with like a sine wave or like kind of wavy shape. Then it's gonna reach to the steady state. So we said that we can break down this time domain or the current function into two domains. One domain is gonna be the steady state part of the time of the current, and this is gonna be the transient. So to end up with the transient and the steady state, to end up with both of them, we have to work on the time domain as already given here. Like we have to end up with the current as a function of time, and this is what we did in chapter 4. And we found that when we even did it for some simple electrical circuit that just include three electrical elements, the capacitor, inductors, and the resistor in one electrical circuit, we're gonna end up with a second order ODE that shall be solved for the current. And we found even when we discussed the analytical solution of this second order ODE, like it is a long trip and it takes time to end up with the transient solution, then the steady state solution basically. And so you could say that to figure out or to do analysis for the electrical circuit in the time domain, it is long journey. It is challenging method, but we can do it basically since we already having some other software like that we can use, like the MATLAB, as we already practiced or knew how we can use MATLAB for building a code to drive the analytical solution for first order ODE or a second order ODE for the electrical circuit. But as a matter of fact, what happened to the transient behavior of the current or the voltage even, that it die out very quick, it vanished very quick. Like if we gonna consider the time period over which we're gonna have the transient behavior of the current, this time period, if we just gonna give it like T stands for transient, and we do have the other time period for the steady state, the time period for the steady state, it is very long period. It means that it's gonna take long time. The rest of the function or the time working of the electrical circuit is gonna be the steady state, and the transient period is gonna die out very quick. It's gonna be finished very quick. And this happens at the instant we just initiate or start the flow of the current within the electrical circuit, but this basically takes portions of a second, part of a second, a few things of the second, and it quickly, the transient behavior, quickly it dies out and it is vanished very quick, and the remaining time of the cyclic work of the electrical circuit, that the current will be behaving based on its steady state behavior or based on the steady state region. So you could say that the contribution of the transient part in comparison to the contribution of the steady state, it is very negligible. Why? The main reason that it dies out very quick. So that's why the focus of this chapter is to know how we can study the steady state behavior and focus more on the steady state behavior with within this region for the current or the circuit response for the electrical circuit, which is going to be definitely in one of the cases going to be the current, but in the steady state. Okay, so we are interested in this one, this steady state. The main reason is that the remaining time period, working period of the electrical circuit, the current behaves based on its steady state behavior. Why? The main reason is that the transient behavior of the current, it dies out, it vanishes very quick. It is going to take a few portions of the second and it's gonna die out, and the rest of the time of the electrical circuit working is gonna be just for the steady state behavior of the electrical of the current, and that's why the focus is gonna be through the chapter on the steady state. So one would say, okay, we started even in chapter 4 and we knew how we can end up with a complete function for the current that would include the transient plus the steady state, and this is what we did. The function, the current function that we drive it for any specific electrical circuit, wherever you drive this solution analytically or even using the MATLAB code, we end up with a current function, and when we try to plot this function, we're going to end up with some wavy behavior. So we end up with both of them, with the transient behavior plus the steady state behavior. So we already have the behavior, we already have the function. So why should we study a new chapter and focus more on the steady state? This indicates that to do analysis for steady state analysis for electrical circuit, we can come up with more simple methods that more suits the analysis in the steady state behavior of the current or the electrical circuit in the steady state region. And this is what we're going to focus on. As you remember in chapter 4, we faced problem, or it is not straightforward method to drive an analytical solution for the transient behavior or the general function of the current as a function of time. In the time, if we're already working in the time domain, as we used to do in chapter 4, it is a challenging method and it's going to take time, especially if we're already working analytically by hand. And especially if it is second order ODE. And all the examples and the problem that we consider even or cover in chapter 4 were very straightforward examples, very simple, the simplest form of the electrical circuit. This is what we consider. But how about if we do have more complicated electrical circuit? So we're going to end up with, it is not just one equation. We solve it analytically in case that the electrical circuit equation is just one equation. How about if we do have 2 or 3 or 5 equations that describe the electrical circuit, and all of these equations are ordinary differential equation, whatever, first order, second order ODE. To solve this system of differential equation, it won't gonna be possible, or it's gonna be very complicated in terms of the analytical working or analytical or in terms of mathematics. So to avoid these difficulties, and as long as we are interested just for more on the steady state, and this is the dominant behavior of the current or the voltage within the electrical circuit, we do have other approaches, we do have other mathematical methods to do analysis for the steady state behavior of the current or the electrical circuit. And this is what we're going to focus on within this chapter 5. So the chapter 5, again, we're going to focus on the steady state, but we're going to use another approach that is different that we already used in chapter 4. Why? The reason is that the approach that we used in chapter 4, it is kind of complicated, especially, and it's going to be very harsh to deal with it or use it for more complicated electrical circuit. So we're going to introduce another approach, another method for solving for the steady state. But this method, it is just suitable for the steady state behavior of the electrical circuit. But if we are interested in the transient behavior, we have to work like chapter 4. But if we're just interested in the steady state, it is recommended with the new method that we are going to discuss through chapter 5. Make sense? You should understand the difference between these two different things. And again, the objective is on the focus is on the steady state analysis of the electrical circuit. And we're going to focus more on the sinusoidal electrical circuit. So what does it mean, sinusoidal? It means that for these electrical circuits that we are going to consider through chapter 5, we're going to consider that the voltage source, it has a sinusoidal waveform. Like it has like this type of form. This is a sinusoidal waveform. Like it's going increase till a maximum value. This is Vm. Vm stands for the peak or the maximum value of the voltage. which could be considered as the amplitude. This is the amplitude value. Then it's going to decrease again to the zero, and it's gonna switch the other side with the same magnitude or the same peak value. So this is the maximum, this is the peak, and this is another peak. This height and this height should be identical. Then it's going to repeat the cycle one more time. So this, you could consider that starting from this point up to this point, going all the way in this way, this is going to give us one cycle. Then this cycle is going to be repeated. The time for one cycle, this is known as the periodic time, if you remember from the physics class. But basically, this is the time of this is the form of the voltage source that we are going to consider for the electrical circuit. So all the electrical circuit that we are going to consider through chapter 5, that we're going to assume that the voltage source, it is of the sinusoidal form, and it has this wavy behavior over the time, right? So as a result, since the voltage is already having a sinusoidal form, we are expecting as well that the current is going to have the same form. It's going to have a similar form. It is not exactly the same form, but it's going to also have a sinusoidal waveform. The sinusoidal, by the way, the sinusoidal word here, don't be confused that this word indicates just only sine function. No. The sinusoidal wave, it would be cosine or it would be sine. So this is like harmonic function, like have this wavy. So we are talking this type of wave. This wave is a sinusoidal wave. This doesn't mean that it is with a sine function. No, it would be with sine function or described as a sine function or even a cosine function. Even the thing that you should understand, we're gonna focus or we're gonna use all the time through this through this chapter, the cosine function. Even if we do have a sine function, we're gonna convert it into its equivalent cosine function, as I'm gonna show you. So this is the general form, but let us go over the different components of this form. We discussed this one. We said that this is the magnitude. This is the amplitude value. This is the maximum value. This is the big value of the volt. Like the volt is going to start from zero and is going to increase to a maximum value, then it's going to decrease to zero again. Then it's going to switch the direction on the other side with the same value, with the same up to the same maximum value. Then it's going to decrease to the zero one more time. So these big values are Vm, which should be this number. Then we're gonna have this as the function, the trigonometric function. We said that it would be sine or cosine. If it is sine, we're gonna convert it back again to the cosine, as I'm gonna show you. So we're gonna focus more on the sine or the cosine trigonometric function to represent this sinusoidal wave. And this omega, this is like the forcing frequency as we discussed in chapter 4. So this is the angular frequency of this wave. And since this is input, this is the source, this is the thing that is going to generate the current within the electrical circuit. So this omega, this natural frequency, this is the angular frequency of the source, of the forcing term itself. And it should be in radian per second. Theta, this is what we're gonna call as phase angle. And this is what we're gonna depend on through this chapter 2, and this is the main idea of, or this angle is the main idea behind the approach or the method that we're going to use for solving for the steady state analysis for the electrical circuit through chapter 5 or this chapter. Make sense? So this angle is known as the phase angle. This phase angle, very quick, it defines like the how we are going to change. For example, like in this case, we start from zero, then the voltage is going to increase to be maximum, then it's going to decrease. We may have another wave, that start from zero, from the same point, but instead of going up, it's gonna start to go down. So you could say that the brown phase, it is the inverted form of the original blue phase wave, right? So we do have like two inverted phase. So inverted phase, it means that there is, inverted waves. So we're gonna say that we do have a phase difference between them. Like this blue wave, it has a phase angle theta with a certain value. This one has a different angle theta. This theta is going to be the negative of this one. If they already identical in everything except that this one at the instant that the blue wave already going up, the brown wave already going down. So there is a difference between in the phase. They do have the same magnitude. They do have the same frequency, the same omega, but they different in the theta value. This Vm for both waves are identical. Omega are identical except the theta. So theta, it is related to the way by which this wave is going to behave or change over time. So that's why also it is one of the essential parameters that should be considered to describe any sinusoidal wave. And this parameter is the main thing behind the method, as I mentioned, that we're going to use for this chapter to do analysis for a steady state electrical circuit, or a steady state analysis for the electrical circuit. We discussed angular frequency, which is radian per second, and we discussed this one in the previous chapter, that this is how fast this wave is going to vary or change over time. But the frequency in general can be defined as the number of cycles completed in 1 second, which could be considered as the revolution or cycle per second, or hertz, which is equivalent to cycle per second. So this is the hertz. This hertz is going to be, or the frequency is going to be the omega, which is the angular frequency divided by the 2 pi, and it's going to be equivalent to 1 over t, where t, this is the periodic time, which is the time of a one complete cycle. How long that this wave is going to take to finish one cycle, this is the periodic time, which is t, which should be the time distance between, or the time difference between these two peaks, or any two similar points belong to the same wave over two consequent cycles of the wave. Make sense? So I'm pretty sure that you had an idea about these things before in the physics class, but this is the thing that we're gonna depend on, or we're gonna assume through this chapter, that all the time the voltage source is going to be in the sinusoidal form. And that's why the title of this chapter is the steady state analysis of sinusoid, or the steady state sinusoidal analysis. It means that we're going to focus on the steady state behavior of the current, or the variable, the main variable of the electrical circuit. In addition, we're going to assume that this electrical circuit is already powered by a sinusoidal wave, or a voltage source of the sinusoidal form. Make sense? So this is for this part. Since we are talking about the sinusoidal wave, how about, by the way, we said that the sinusoidal doesn't mean that it is necessary to be the sine form of, or the function that describe the voltage should be in the sine function, at the trigonometric function. No, we're gonna focus, or we're gonna use, this is what we're gonna assume all the time through this chapter, we're gonna depend on the cosine more than even the sine. But both the sine and the cosine, both are sinusoidal functions. Okay, so in case, how about if the voltage is already given in the sine form? So we're gonna consider this identity that relates the sine function to the cosine function. Like the sine of any angle, it is equivalent to the cosine of the same angle, but negative or plus the 90 degree. Because as you remember that the cosine, it just get rid of the negative sign. So you're just gonna add negative 90 to this angle, you're gonna end up with the value that is equivalent to the sine function. So this is how you can convert a sine function into an equivalent cosine function. So for example, if the voltage source is already given as 10 sine 200, again, remember that this 200, this is omega. This is the angular frequency, and this is the time, this is theta, which is the phase angle, and this is the magnitude, the peak. This is the magnitude or the amplitude of the voltage. This is the peak value of the voltage. So how about if you would like, and here it is given in the sine form, how about if you decided to convert it into cosine? Your objective is just to add to all of this angle, all of this thing. The angle here, it is omega t plus theta. This is the angle. All of it, it is the angle. So your objective is just to add negative 90 to this angle. Adding 30 negative 90, this is going to give us negative 60. So this is the equivalent form to the original form. This is the sine. Now I'm going to work with the cosine, and this is what we're going to use in the approach that we are going to discuss through the chapter. Make sense? And here the phase angle of this volt is going to be considered as negative 60. So, and this is what we're going to depend. For example, for this one, what is the phase? If you have been asked, this is what we given. This is the given voltage function. And how about if I ask you, what is the phase angle for this function? The phase angle for this function, you could consider that this is theta dash. The phase angle that we need in this chapter, it should be the phase angle for the cosine form, not the sine form. This is the sine form. This is the sine function. We have to convert it first into its equivalent cosine function. Then we're going to come up with the phase, how much it is. So the phase here it is -60, and this is the phase that we're going to depend on our method that we're going to use for chapter 5. Make sense? Since another thing here that we need to discuss before we go through, today we won't going to discuss the method with more detail, but we just introducing to this method, which is known as the phasor method, that depend on using phasors and define phasors. So to understand phasors, it is related definitely to this phase angle. So that's why we're already introducing some things and concepts so you could understand this method, right? So since we are dealing with a voltage and this voltage is going to change over time, one of the challenges, this indicates, for example, that the electrical power itself is going to be varying over time. It won't gonna be fixed, right? But in terms of practical use of electrical circuit, so the power, as we mentioned, for example, if we assume that you do have a resistor, and over this resistor there is a current I of t, and there is a voltage source between the two ends of this resistor, which should be definitely V of t. So as we agreed in this chapter, we're gonna focus on the sinusoidal voltage source. It means that V of t is gonna be given in the sinusoidal wave. It means that it is already varying over time. So if I ask you to calculate the electrical power, as we discussed even from chapter 1, the electrical power is gonna be with this form. The power is gonna be V squared divided by R. R is just a constant value. This is the ohms of the resistor itself, and it's going to be the square of the voltage. So this indicates that the power itself, it is also a function of time. It is not a constant value. It is already varying over time. But in terms of the practical use of these electrical elements and this electrical circuit, we have varying power. It means that we need to describe the power with a constant value, with a suitable value that it should be constant and it shouldn't be varying over time, because it doesn't make sense practically speaking. I'm talking about the practical use of this electrical circuit. It is not convenient to represent the power of an electrical circuit as a function of time. No, but we need a value that gives that this electrical circuit had this power, and this electrical circuit has a different power, and so on. So what is this power value? In the practical use, this power, the actual power, it is varying over time. It is not constant, but we need a value to describe the power, a constant value that would describe or would be convenient to describe the power or the equivalent power of an electrical circuit with sinusoidal voltage source at the case that we are going to consider. So that's why we're already discussing this part here. So it is highly acceptable to represent the power of an electrical circuit as the average of this varying power. The power, the actual, it is changing over time, but it is highly acceptable to take the average value to describe the equivalent power for this electrical circuit. And this is what we are interested in. What we are interested now for this slide is to show you how we can calculate the average electrical power for any electrical circuit with sinusoidal voltage source. So for this case, if we can calculate the energy, the total energy, which it should be the integration over the time period. Here we're just gonna pick, because this voltage is already changing over time with multiple cycles, right? So this is gonna be the t, this is gonna be v of t. So we're gonna have here multiple cycles of this wave. So let us pick just one cycle. If we choose only one cycle like this one, what is the time period of this one? It should be t uppercase, which is the periodic time that we defined up there, right? This is the t. Make sense? This t, which is this one. So using this t, and let us integrate the power over this periodic time. This definitely is going to give us the electric energy. This is going to give us the energy delivered within one cycle of the volt. If this volt source is just one cycle, how much of energy that this source gives us through the electrical circuit is going to be E, the integration from 0 to t uppercase, which is the periodic time, the power dt. If we did the integration, we're going to end up with, and then we can, from this energy, we can calculate the average power. The average power definitely is going to be this energy, this total energy within one cycle, and the power is already changing because the voltage is already sinusoidal function over the periodic time. So this value, this expression, this gives the average power, and it is acceptable, as I mentioned, to describe the power of an electrical circuit using its average power value. And this is what we're going to do. So this average power is going to be the total energy within one cycle of the voltage source per the periodic time. But how about if you do have two cycles and you did this one over two cycles, you're going to have here 2t. So it's going to end up with the same average power. It means that this average power, it is describing the average electric power over the complete cycles, over all the cycles of the voltage. Because if you consider two cycles, so you're going to divide by 2. If you consider 3 cycles, you're going to divide by 3. You're going to end up anyway by the same average value. This average value is going to be 1 over t, the integration from 0 to t, b of t dt. You're just going to plug e, this term here, and doing the integration and plug this v here for the power. If we're going to end up with this expression, this integration term here with the 1 over t, all of this entire term, if we just remove this r outside, is going to give this term. This term is known as the root mean square of the voltage, of the periodic voltage V of t. This is known from the statistics class or even from the mathematics and the physics class, that the root mean square of any quantity that already valued over time, like this case, is going to be the average by taking the average of its squares. So it is the root mean square of, which is commonly known as the RMS, which stands for the root mean square of the volt. This root mean square, which is going to be this value. So if we do have this value of the root mean square of the voltage source, that already of the sinusoidal form, we can calculate the average power using the root mean square, the V, root mean square, the square of this one divided by R. This is going to give us the electrical power over a resistor at the average power, because the actual power, as we mentioned, it is already varying with time, but this is the average one. We can do the same for the current. How about the current? The current also is already changing over time. And remember that we can represent the power, the electric power, as a function of t. It can be represented in terms of the, so this is the power in terms of the volt as V square over R, but the power, the electric power, in terms of the current, it should be I of t square times R, right? So the power, if you decide, if you already given the current, here if I already given the voltage, I can calculate the electrical power. If I already given the current, or you do have the current value, you can calculate the power. But the power is going to be as well function of time. If you would like to describe the power, the average power, or come up with the average power, you can define this average power. If we did the same procedure and the same analysis, we're going to end up with a very similar equation for the average power as I square R, where this I square, it should be the root mean square of the current function that already given to us. And this root mean square current is going to be the same formula as the voltage, typically the same. So it doesn't matter whatever it is, volt or current. As you can see, the average electric power that is going to be generated due to a voltage source or a current source, because the source, it would be current. Here the source, it is a voltage source, but we may have the source as a current source. So for a current source or a voltage source that already varying over time, how much of average power that this source is going to give us, it depends on the root mean square of this source, of the volt or the current of the voltage source or the current source, divided or multiplied times R, which is the resistance over of the resistor. Make sense? So now we would like to calculate the root mean square voltage and the root mean square current of any sinusoidal wave. If we assume a voltage or even a current, the same thing can be applied to the current. If you do have a voltage source like this one with the cosine form, with the sinusoidal form, if it wasn't sine, you're going to convert it first into the cosine form, then we're going to work using the cosine. If we plug this one into this expression, we defined here the root mean square for the voltage as 1 over t. What is t again? This is the periodic time. The integration from 0 to t, which is the periodic time of one cycle, v squared dt. So we're going to plug v here into this integration form to do the integration, and this is what we're going to do here. So substituting into this expression for the v root mean square, plug v square, we're going to end up, this v is going to be v square the cosine is going to be cosine squared dt. Doing the integration, there are lots of mathematics. It is not needed even to know the calculation and the mathematics and the integration, how we already did it. But at the end, if you even using MATLAB or even you follow this mathematic things, you're going to end up with this root mean square value. So generally speaking, for any sinusoidal voltage source, the root mean square voltage, it is the peak of the voltage source, which is this Vm value divided by the square root of 2. Square root of 2 is 1 over square root of 2 gives 0.7071 times the peak value. So for example, if you already given the V of t as 10 cosine 3t negative 30 degrees. So what is the root mean square value? The root mean square value of this voltage source is going to be the peak value, which is 10 divided by square root of 2, and do the calculation in terms of volt, and that's it. Make sense? It means that there is no need anymore to do these integration things. Automatically, for any voltage source in the sinusoidal form, in the cosine form, its root mean square voltage value is going to be the peak, its peak value divided by the square root of 2. The same thing applies to the current. How about if the current is the one that is already given as a sinusoidal form as a cosine function? So automatically it's going to be its peak value, its coefficient of the cosine function divided by the square root of 2. This automatically is going to give us the root mean square of the current function. Make sense? So for example, so using these definitions, we can simply doing the calculation for the electric power. So let us consider this example here, this very quick example. How about if the V of t is already given by 10 cosine 4t negative 40 degrees. So this is the volt. It is required to find the electric power, how much it is as a function of time, and the average power, how much it is. For this voltage that already going over the resistor with the resistance R, and R is already given by, for example, 10 ohms. So simply to calculate the power function, the power P of t, it should equal to the V square of t divided by R, right? So V square, it means that you're gonna calculate the square of this function. So it's gonna be the t square times the cosine square of 4t negative 40 divided by 10. This is gonna give us the 10, the cosine square of 4t negative 40. Make sense? Then the cosine square, it should be converted into its equivalent, either sine or the cosine. We need to get rid of the square. So to do so, we do have this identity here, that this cosine square of a function, it is equivalent to 1 plus the cosine of double the angle. Like the cosine, you're going to consider this identity, like the cosine of x. The cosine square of x is going to equal to the 1 plus the cosine of 2x. Just to get rid of this square. So doing so here, we're going to end up with this expression like 10. The cosine square is going to be the 1 plus the cosine of double this angle, which is going to be 8t negative 80 degrees. This is going to give us automatically the power as a function of t. This is the power function. How about the average power? The average power, as we define it up there, it should equal to the root mean square, the VRM square, the root mean square of the volt squared divided by R, right? So it means that we have to calculate the root mean square of the voltage source, which is already given by, it should equal to the peak value divided by the square root of 2. So the peak value is already given by 10 divided by 2. Doing the calculations, you're going to end up with 10 divided by square root of 2. This is going to give us the 7.071. Make sense? Volts. Then you're just going to plug this one here. You're going to end up with the average power, which it should equal to the 7.071 squared divided by R. What is R? It should be equal to 10 ohms as already given up there. So doing the calculations, we're going to end up with electric power as 5 watts. This is the average electric power, and this is the, in terms of watt, and this is the electric power as a function of time. So this is the power, how it's going to change over time, but this is its equivalent average value. Make sense? So this is for the first part of this chapter, is just to understand what does it mean a sinusoidal wave. And remember that all the time we're going to depend on the cosine function form. And if it is already given in the sine, we discuss the approach. You're just going to add negative 90 to the angle. You're going to directly convert the sine function into an equivalent cosine function. And the focus through this chapter is again to do analysis, steady state analysis for electrical circuit with a sinusoidal wave, or basically the current, the voltage source, or even the current source is going to be in the form of a sinusoidal wave, and this is going to be the focus of this chapter. As we discussed in the beginning of this video, that we're going to use a special or a new method or a new approach to come up with or do analysis, steady state analysis for this electrical circuit. And this approach depends on the phase angles and depends somehow on representing or rewriting again the electrical circuit, or coming up with an equivalent electrical circuit but in another domain that is different than the time domain. If we're already working in the time domain, it means that you're already dealing with the time as we're already using here, and as we already did in chapter 4, we said that this is a long trend, and it's going to be clear as we move through this chapter, right? But now we need to do like kind of conversion. We need to convert this electrical circuit and move it from the time domain into another domain. And when we try to solve this electrical circuit in the new domain, we're gonna get rid of the difficulty that we used to face in the chapter in the time domain. In the time domain, when we do analysis to the electrical circuit, as we discussed, we're gonna end up with some differential equations. And if you do have multiple differential equations, it's gonna be much more difficult to handle them or to solve them analytically. But if we move the electrical circuit to another domain, and this is what we're going to discuss through this chapter, and we're going to show you how you can switch to another domain, we could end up with the electric circuit is going to be linear algebraic equation or simple algebraic equation. There is no differential equations anymore, so we can solve this equation analytically. And this is what we're going to do through this chapter. Or you could say that through the chapter, we're going to give you a method of converting the original electrical circuit into another equivalent resistive circuit. We started in chapter 2 and we found that it is much way easy for us to solve any resistive circuit with the four methods that we discussed, right? We didn't experience any differential equations in chapter 2, right? So can we do so with this electrical circuit that include resistors and capacitors and inductors at once in one electrical circuit? Yes. We can do it, but only under one condition: if we are interested in the steady state behavior of the electrical circuit. But if we are interested in the transient behavior, we have to use the approach. We have no clue, no method except the method that we discussed in chapter 4. But here we're just gonna focus on the steady state. So we're gonna introduce a new method, a better method, simple method to do analysis, but for the steady state analysis for this electrical circuit. Make sense? So to introduce this method to you and understand it, I have to do like a review for the complex number that I think that you have studied these things in the mathematics class before, or even at least in the physics class. So I'm gonna go over like a revision of some mathematics related to the complex number, how we can, what does it mean a complex number, how we can represent the complex number in different methods and approaches, also how we can do some simple algebraic equations or algebraic calculations to this complex number. This is what we're gonna discuss next before we introduce to you the method that shall be used for this chapter. Make sense? All right, so the complex number, it would be represented in different forms. So first we're gonna discuss the different ways of representing a complex number. And one of the things, just to remind you, what does it mean complex number? So let us refer to this number as Z. So Z stands for any number that is in the complex form. And the complex form or the complex number could be represented in the rectangular form. It should be like number value. There should be a number or a value here, plus or minus j, where j, this is the square root of -1, and there should be another number here. So this is a general form of the complex number, this form is known as the rectangular form. Like you're gonna have a number, this number here represented the real part plus or minus the imaginary part of the complex number. So this is a complex number. And there are some identities or things that you should understand about j. This is the square root of -1. Sometimes we would give this j as I, but I am using j here to distinguish between the current, because we used to use I for the current. So to not be confused, the I we refer to the I as a current, but the j here we indicate the square root of -1. And since then the square of j, it should give us the -1, and the j to the power 3, this is gonna give us the negative of square root of -1, which it should give us the, at the end, the negative j. And the j to the power 4, this is gonna give us just 1. Make sense? So these identities that I'm pretty sure that you had an idea about them. And again, this is the rectangular form of a complex number. Like for example, let us consider this example. If you already given z equal 3 negative j5. So this indicates that the real part of the number, of the complex number z, it equals 3. This is its real part, is just 3, and its imaginary part of the z is gonna be the 5 itself. Don't include the -5. I'm sorry, it should be negative. It should be -5, because the j, it should be just j. So the complex number or the imaginary part value is gonna be the -5. And the conjugate of any complex number, the conjugate of the number z is just to switch the sign in the middle here. If it is positive, put it negative. If it is negative, put it positive. And we used to give it like z star. So this star indicates that this is the conjugate of z. It's gonna be the 3 plus j5. Make sense? So these things, I'm pretty sure that some of you already had, or you remember these things from the mathematics or even the physics class before. So this is one form of the complex number. Also, we can represent the complex number, which it should be in equivalent form, but this one is known as the polar form. So this is the complex number, but in the polar form. A complex number in the polar form is going to be represented in this way. It will be like z, this is the complex number. It should be here a value, and then we are adding this angle symbol, and we add here angle in degrees. The angle, it should be in the degrees. Make sense? It shouldn't be in the radian. So this is the z, where this number here indicate the magnitude. This number indicate the amplitude or the magnitude of the magnitude of this wave number, of this complex number, and definitely this is gonna be the angle, and this angle, it should be in degrees, as we said. Make sense? Like for example, we can represent this one in case that we do have like this is the imaginary axis. This is going to be the imaginary axis, and this is going to be the real axis. This is going to be the real axis of the complex number. Then we're gonna have the number like a vector in this direction, where the length of this vector that represents this this complex number, the length of this vector is going to be like 5, and this is going to be the angle like 30 degrees. So to represent this one, this graph or this representation, this indicates a complex number. This is like an example here of a complex number. Z equals the magnitude, which is the length of this line or this vector, is going to be 5. This is the magnitude or the amplitude, and it is inclined with the real part. It should be this real, like this is the x-axis with an angle 30 degree. So this is going to give us the complex number, but in the polar form. Make sense? So this is another way of representing also a complex number. You should understand that this thing, it is a complex number. Make sense? And the magnitude for this number, its magnitude, as we said, its magnitude, it equals 5, or amplitude equals 5, and its angle, which later we're gonna call this one as phase angle. This is gonna be the 30°. Make sense? Now how we can convert from the rectangular form to the polar form, or the opposite, how we can convert from polar to rectangular form. So now let us know how we can convert from polar to rectangular form. Of the complex number. Make sense? Like it is given to us for the case that it is given as z equals the magnitude of z. This is the magnitude of the complex number, and this is gonna be the angle theta itself. This is the polar form it is given, and we would like to convert to a rectangular form. So the rectangular form z is going to be the x plus jy, where x, this is the real part, and y, this is the imaginary value, where the x it should equal to the magnitude of z, the cosine of the angle theta, while the y is going to be the magnitude of z, the sine of the angle theta. This is how we can convert the polar form into an equivalent rectangular form. How about, can we do the opposite? Yes, your objective just for polar, you're going to take the magnitude, this number, cosine the angle, this number, sine the angle, you're going to end up with x and y, plug them here, you're going to end up with the equivalent rectangular form. How about, can we convert from rectangular form, rectangular, to polar form? Yes. So the complex number in the rectangular form would be given in the form as z equals x plus jy, where x, again, this is the real part, y, it is the imaginary part. So to convert into the polar form, we need the magnitude, because the polar form requires the magnitude of z. So this magnitude is going to be the square root of x squared plus y squared. Then you're going to calculate this value. Your objective then is just to find theta. So the theta, it should equal to the tan inverse of the y value, the imaginary value, divided by the real value, which is y over x. Doing these calculations, then you can arrange them, this magnitude into this form, into this polar form, and the magnitude and the angle is going to be theta. This is the polar form. This is the polar form for a given rectangular form. Make sense? So simply, these are two ways of representing the complex number in the rectangular form and the polar form, and we knew how we can convert or switch between both of them. There is a third form here, which is the exponential form of the complex number. So for this type of form, it's going to have like exponential. So in the exponential form z, it's going to be the magnitude or the amplitude, the e, which is the exponential, to the power j theta. So this is the angle and this is the magnitude, very similar to the polar form, but instead of writing like magnitude and angle, and we just put the angle, we just gonna use instead of the angle sign, we're gonna use here the exponential j theta, right? So this is the exponential form of the complex number. Now let us know how we can convert this exponential form into either the rectangular form or into the polar form. So the convert from exponential to rectangular forms, or between the exponential and rectangular form. So if it is already given, if it is given z in the form of magnitude exponential j theta, there is an expanded form for this exponential. Like this exponential can be expanded as z equals the magnitude of z, then you're gonna have the cosine theta plus j sine theta. So the magnitude and this exponential term, the exponential itself, it expanded into cosine plus j sine. If it is negative there, it should be negative. Make sense? So, for example, let us consider an example here. How about if z is already given as 10e to the power 40 degrees? So this is gonna give us, this can be converted into z, its equivalent converted form. Z is gonna be equal to the magnitude, which is 10, then you're gonna open the parentheses, theta. Cosine theta is 40 degrees, and plus j sine theta, which is already 40 degrees. So this is the equivalent rectangular form. So it's the real part of this number, the real part of z is gonna be the 10 cosine 40 degrees, but the imaginary part of the number z is gonna be the 10 sine 40 degrees. Make sense? How about if we do have, let us consider another example here of z is already given by 15 e to the negative j 45 degrees. So this negative, this would have z in the rectangular form will be the magnitude 15. Then we're gonna have the cosine, the angular is 45 degree. The angle should be, by the way, negative 45 degree plus j sine negative 45 degree. One of the characteristics of the cosine function that it gets rid of the negative of the angle. It means that the cosine theta, it is equal to the cosine negative theta, and the sine theta, the sine reject the negative. So this equivalent, this it will be equivalent. Z, it's gonna be 15. The cosine 45 degree, because the cosine takes over or gets rid of the negative, but this sine rejects the negative outside the sine. So it's gonna be negative j sine 45 degrees. Make sense? Now, if I ask you how much is this, the real part of z. So the real number of z is gonna be the 15 cosine 45 degree. This is gonna be the real, and the imaginary definitely of z is gonna be the negative of 15, the sine of 45 degrees. Make sense? So this is simply how we can convert the complex number into an equivalent rectangular form, or the complex number from the exponential form into the rectangular form. Can we convert the complex number in the exponential form into another polar form? Yes. So to convert from exponential, convert from exponential form to polar form. So it is very direct way, like it is given for a given z in this form as magnitude of z and e to the power j theta, its equivalent polar form is going to be z equal to the magnitude, the same value, and instead of using the exponential, you're just going to use the theta. This is a straightforward approach to convert from exponential to the polar form. It is much more simple even than the previous, the rectangular one. So for example, if z is already given to us like 10 e to the power 60 degrees, so this is going to be converted into z equals, the magnitude is still 10 and the angle is just 60 degree. Straightforward thing. Even if it is in negative, this is another example. If z is given by 7 e to the negative j 70 degree, so this is gonna be z equal 7. And remember, by the way, this 10 and 7, this magnitude should be positive anyway. It cannot be negative. The angle, it would be positive or negative. So the angle here, it is negative 70 degree. Make sense? So this is how we can convert from exponential to complex number. Now let us know some operations, how we can do operations over complex number, because we're gonna need this for the phasor analysis method that we're gonna use through this chapter. So let us start with some operation. Now let us discuss the operations on the complex number. So for the complex arithmetics and some of the operations that can be done over complex numbers, starting with the addition and subtraction. This operation, it should be done in the rectangular form of the complex number. It means that if the complex number is given in any other form than the rectangular form, it should be converted, all the number that should be subtracted or added together, we have to convert them into their equivalent rectangular form first. So this operation, it should be performed in the rectangular forms of the complex numbers. Make sense? So, for example, let us consider this example just to show you how we can do this operation. Let us, if Z1 is already given by 10 angle 30 degrees, so this is a polar form of this number, and Z2 is already given by 12 angle negative 60 degrees. So it is required to calculate the sum of Z1, number A, Z1 plus Z2, and for B, it is required to calculate Z1 negative Z2. Make sense? So to solve this problem, first of all, step 1, since we do have these numbers already given in another form than the rectangular form, it should be converted into rectangular form. So I have to convert, this is going to be the first step, to rectangular form. Make sense? So the rectangular form, it means that what is the equivalent rectangular form to Z1? Z1 is already given by the magnitude, is already given by 10, the angle is 30 degrees in the polar form. So it can be converted at the 10, the cosine of 30 degrees plus the J, 10 sine 30 degrees. We said this is like the X, which the X, it should be the magnitude, the cosine, the angle, and the Y is going to be the magnitude, sine, the angle directly. Make sense? So doing the calculations, we're going to end up with 5 square root of 3, to this term, plus J, the 10 sine 30 gives 5. Do the same for Z2. The magnitude is 12. The cosine of the angle, so it's going to be the cosine of negative 60 degrees. I remember the cosine, it gets rid of the negative sign, plus the J. The magnitude is 12, so this is the first real term, 12, the sine of negative 60 degree. We can get rid of this or reject this negative outside the J, so it's going to be negative here, or even you can include it in the calculator during the calculation. So anyway, we're going to end up with 6, which is this time, the 12 cosine 60, the negative, that's why this negative had been rejected, J 6 square root of 3, this is going to give us the Z2. Now we have to add them. To add them in the rectangular form, so step 2 is just to perform the operation. Step 2, perform the operation that already required. It is required to add them and subtract them. So the first operation is Z1 plus Z2. So it is Z1 plus Z2. When we add, your objective is just to add the real numbers plus and then add the imaginary. It means that the real should be added together than the imaginary. So the real number here for the Z1, it is 5 square root of 3 plus the real number, which is 6, plus J. Then you're just gonna add the imaginary number. The first imaginary number is 5 negative 6 square root of 3. This is the other imaginary number for the other complex number, right? So your objective is just to add here, add real numbers, and then you're just gonna add here the imaginary, add the imaginary numbers. You can directly end up with this value for this is going to be the complex number, which should be the addition of z1 plus z2. This is going to give us any you can do even the calculation. For the subtraction, z1 negative z2. This is going to give us, you're going to do the same. Instead of adding, you're already subtracting z negative z2, z1. So z1 first should be positive, negative the real of the z2 plus j, the real, the imaginary of z1, negative the imaginary of this one. So negative times negative gives positive 6 square root of 3. This is going to give us the same thing for the real number, the subtraction of z1 negative z2. So this is how we can perform addition or subtraction to complex number. Again, these complex numbers should be in the rectangular form. If they already given in a polar form, exponential form, we discussed 3 forms: rectangular, polar, and exponential form. Your objective is just to convert them back into the rectangular form first, then you're gonna do the addition or subtraction over these numbers in the rectangular form. Make sense? Now let us move to the multiplication, another operation. So operation number 2 is the multiplication or addition and division of complex numbers. So to perform this can be done in the multiplication or division of two complex number can be performed in the polar form or in the exponential form. It is better to do them in the polar form or the exponential form. So the multiplication or division of two complex numbers can be performed in either the polar form or the exponential form. Make sense? So for example, let us consider these different examples here. How about let us consider like case 1. How about if z1 is already given at the magnitude of z1 e j theta 1. So it is already given in the exponential form, and z2 is already given also in the exponential form as z2, the magnitude of z2 e j theta 2. Two complex number in the exponential form. So their multiplication or their division, so the multiplication of z1 cross z2, this crosser is not cross vector. We just consider this one like it is scalar multiplication kind of, but it should be like vector multiplication in fact. But anyway, so your objective, you're just gonna do the multiplication of the magnitudes. So the magnitude z1 will be multiplied times the magnitude of z2. Then you're just gonna add the angle. The angle will be added. So this is gonna give us the exponential of j to the power of theta 1 plus theta 2. So your objective here for the multiplication, you're just gonna add angles, but you're just gonna multiply, this is for the multiplication, multiply magnitudes. Make sense? This is how we can do the multiplication of two complex number that already given in the exponential form. How about if they already given in the polar form? It's going to be the same. So case 2, how about if z1 is already given at the magnitude of z1 and the angle theta 1, this is a polar form. Also z2 is given at the magnitude of z2 and the angle is theta 2. And we are interested in their multiplication. So the multiplication is going to be z1 cross z2 equals, you're going to do again the multiplication of the magnitudes, and then you're going to add the angles together like theta 1 plus theta 2. So you're just going to add the angles, add angles, and just multiply magnitudes. Make sense? So this is for this case, in case that the two complex number already given in the polar form. How about the division? The division, instead of multiplying, you're gonna divide and you're gonna subtract. So for example, like case 3, so if Z1 is already given at the magnitude of Z1 and E, J, theta 1, and Z2 is already given at the magnitude of Z2, E, J, theta 2. So how much is the Z1 divided by Z2? So for the division, you're just gonna do the division considering which one on the top, which one on the denominator, doing the same. So it's gonna be the Z1 divided, the magnitude of Z1 divided by the magnitude of Z2, and then you are going to subtract. Z1 is on the numerator, so it should be theta 1 negative the angle of the complex number that is located in the denominator, which is Z2. So it should be theta 1 negative theta 2. So your objective is just to subtract angles and divide the magnitudes. The same thing applies for the complex, for the polar form. In case that it is already given in the polar form, you're just gonna do the same. For the polar form, you're just gonna divide the magnitudes and you're gonna subtract the angles. This is how we can perform the multiplication or division for two complex number. Also, we discussed before the addition and subtraction of two complex number. The thing in the addition and subtraction, that it should be performed in the rectangular coordinates, but the multiplication and division, it can be done in any form, but it is much way recommended in the complex form and in the the polar form or the exponential form. Make sense? So this is for, we can do it even, we can do the multiplication in the rectangular form, but it is a long trip. It is much way easy if we did the multiplication and division in the exponential form or the polar form. Simply we're just gonna add or subtract the angle, do the multiplication for the magnitude or the division, depending on whatever it is, multiplication function or it is division function. Make sense? So this is for the complex number. And this is like introduction to this chapter. We introduce for this chapter, and again the objective is just to do steady state analysis for electrical circuit that include sinusoidal behavior of the voltage or the and the current. And to do so, since we are interested in the steady state, we said that we're gonna introduce new method. To understand this method, we have to have like a revision over the complex number and how we can represent them in different forms. Also how we can perform these simple arithmetic calculations like the addition, subtraction, multiplication, and division as we discussed over the complex number. That's it for this video. The next video, we're gonna introduce the new method that we're gonna use for the analysis of electrical circuit, which depends on the phasors, which is known as the complex phasor method. And this is what we're gonna discuss in the next video. Thank you and see you in the next lecture.